So today we will be continuing our discussion with phase conversion. Phase conversion means generally you have three-phase supply available to you. So in case you require some 6-phase supply, 12-phase supply or 2-phase supply, and why not 4-phase supply like that, one can achieve that by connecting transformers in a particular way. So 3-phase to 6-phase conversion can be obtained by star double star connection, that is YY0, YY6 like that, delta double delta connection. Now today I will tell you how to get 2-phase supply, balanced 2-phase supply, given that balanced 3-phase supply from balanced 3-phase supply. This can be done by using two single-phase transformers. Two single-phase transformers. One transformer is called main transformer, whose turns ratios are suppose N1 is to N2, primary and secondary. And this main transformer must have a 50% tapping. And main transformer N1 is to turns ratio with a tapping on primary side at 50%. And then there will be another single phase transformer, single phase main transformer. Another single phase transformer will be required, which is called a teaser transformer. Or auxiliary transformer, whatever you call. And it should have a number of turns as root 3 by N1 is to N2. That is primary number of turns if for the main transformer is N1, for the teaser transformer it should be root 3 by 2 into N1 and N2. We will see why it is like that. Now how these transformers are to be connected. Suppose the connection. What you do is this, first you draw the main transformer primary, and suppose this is its secondary. Okay, this is the main transformer, and as I told you, it will have a 50% tapping. Total number of turns N1. And the auxiliary transformer or teaser transformer, I just draw like this. It will have its primary and secondary. So these are primary and secondary of the teaser transformer, and these are primary and secondary of the auxiliary transformer. Now suppose I name the transformer like this. Terminals are like this, A1, A2. And its corresponding secondaries are A1, A2. This is one transformer. Similarly, this one I will name it as B1, B2 with a center tap at O. These are the three terminals for the primary, and for the secondaries you have got see B1, B2. Like this. Now what you do, and remember the number of turns here is root 3 by 2 into N1, and this total number of turns between B1 and B2 capital is N1, and here it is N2, here it is N2 like this. Now this you join, the connection I am doing now, and these three wires you take from the three free terminals now available to us to energize the transformer from a balanced three-phase supply. Suppose the supply given is A, B and C. And suppose as told earlier, these are dots here, B1, B1 dots. Now if you give a three-phase supply, the input supply phasors, if you look at, it will be like this. This is A, this is B, this is C. And obviously A is joined with A1, so this is A1. Similarly, C is joined with B1, this is B1, and B, supply B is joined with B2, this is B2. Okay, now let us take one transformer at a time. The voltage applied across the primary of the first transformer is voltage between B1, B2, that is BC phasor, this phasor. Voltage applied to the primary of the main transformer. Therefore, its induced voltage on the secondary side will be like this one, B1, B2, parallel to this. And its magnitude of this voltage will be, if the line-to-line voltage is V, suppose V is equal to applied line-to-line voltage, then this magnitude will be V by N1 into N2, this length. Now the question is, how much is the voltage applied to the primary of the teaser transformer? Remember that the primary of the main transformer receives this voltage, and this is the center tap. Therefore, voltage induced in this portion and in this portion of the main transformer, they will be in phase. The sum of these two makes this one. Therefore, from this, if I subtract this voltage, that is this point O will lie here. Therefore, the voltage applied across the primary of the teaser transformer between A1 and O will be this vertical line. This vertical line. This must be understood. Because the same flux is flowing here. Therefore, induced voltage OB2 and OB1, they will be cophasal. Same flux is linking. So, AO, this length is the voltage applied across the primary of the teaser transformer. So, how much is the voltage applied? Line to line voltage I have assumed V. So, this length will be definitely root 3 by 2 into V, because this is 60 degree. So, this voltage applied is root 3 by 2 into V. What is the voltage per turn of the teaser transformer? V by N1. What is the voltage turn of the main transformer? V by N1. It is precisely for this reason the number of turns of the teaser transformer is also made root 3 by 2 into N1, such that the induced voltage on the secondary of the teaser transformer will be now a phasor parallel to this, and its length will be also like this, V by N1 into N2. In fact, that root 3 by 2 gets cancelled. Root 3 by 2 into V divided by root 3 by 2 into N1 into N2. So, this length and this length will be equal. But this angle being 90 degree, these two voltages will be shifted by 90 degree. So, you now get across these secondaries of the main and auxiliary transformer two voltages whose magnitudes are equal and they are time displaced by 90 degree. Therefore, we call it a balanced two-phase supply. Okay, balanced two-phase supply. Now, after all, you have generated this or tried to get this balanced two-phase supply in order to supply a balanced two-phase load. Suppose balanced two-phase supply may be necessary to run a two-phase motor. See, there may be three-phase motors available, two-phase motors available, which are used in control system. or also it may be necessary to supply a two-phase furnace. So those kinds of loads require two-phase supply. Of course, it does not mean there cannot be a three-phase furnace like that. I don't want to mean that. But there are situations where you may require two-phase balanced supply to run a balanced two-phase motors, say control motors like that. So anyway, in order to supply that load, what you do now, you join this A2 and B1. You join such that this becomes your neutral point of the secondary, and where you will connect load. Load will be, this is the two phases and this is the neutral on the secondary side, which I write with a small n, and then you will connect load here. Okay, then the transformer will be loaded and there will be reflected current on the primary side and it will draw power from your three-phase side. So this is balanced three-phase supply. All are B, three-phase supply. Now the question is how to calculate the currents. Obviously, the moment you join A2, B1, these two phasors gets like this after this connection on the secondary side. It will be like this, A1, A2, and then this B1 you shift parallel, B1, A2 are joined, and this is B2. After this A2 and B1 are joined, it will be this one. Obviously, the line-to-line voltage will be √2 times the phase voltage. This one is √2 times this. This is obvious. So line-to-line voltage, whether it has been properly connected or not, can be easily verified by measuring with a voltmeter this voltage and this voltage. They should maintain a relationship of √2 in case of two-phase system. So this connection we have made. Now let us see how to calculate the currents. Suppose the secondary load, secondary two-phase load is balanced. And power factor is, suppose, cosine theta lagging. Okay. Then the secondary currents on the secondary side, it will be like this. This is the secondary voltages. This is B2, this is B1, this is A2 also, and this is A1. These lengths are all equal. So secondary currents will be in this way. That is IA bar, it will lag by angle theta, and similarly this will be IB bar, it will lag by an angle theta, if the power factor angle is theta on the secondary side. And obviously the magnitude of IA bar and IB bar will be same. So I can write it like this, IA bar magnitude is equal to IB bar, because of the fact the load is balanced on the secondary side. The problem is to calculate the primary currents. The problem is how to calculate the primary currents. So to do that, I will not once again draw, but come to look at this diagram once again. So here I have assumed this current is IA bar and this current is IB bar, and there will be some reflected current on the primary side. Let us assume that the primary currents are IA bar, IB bar, and IC bar. What is the IA, IB and IC should be such that the MMF are balanced in each of the transformers. Is not? We neglect that no load current business. So this reflected current because of IA will be decided by the MMF balance. For example, so far as the teaser transformer or auxiliary transformer is concerned, the calculation is very simple. This is a transformer with its own magnetic circuit. Therefore, MMF on the secondary side and primary side must be equal. So, what will be the equation? The equation will be root 3 by 2 into N1 into IA bar should be equal to N2 into small IA bar. IA bar is known on the secondary side. IA bar is known. What will be? Capital IA bar. Okay. So this will be the first equation. So the first equation is therefore root 3 by 2 balancing the MMF root 3 by 2 N1 into IA bar is equal to N2 into IA small bar, or IA bar is therefore known. It will be 2 by root 3 into N2 by N1 into IA bar. So IA bar can be completely calculated, and it will be in phase with IA bar. Okay, so this one will be, if I have to draw IA bar, I will draw it like this, parallel to this line here somewhere. IA bar I will draw. Its length is this one. Now the calculation of the current of IB and IC is slightly tricky, in the sense that, remember, of course the fact remains that we have to balance the MMF, that's all. So in this case, just to once again recapitulate, how do I write this equation? The current is coming out from the dot, IA bar, therefore there will be current coming in from the dot here. So these two MMF must balance such that the flux gets nullified, etc. Similarly here, see this B1 are dot. Obviously the other terminals are dot, equally I can treat it, as you know, this one will be equal thing, is not? One pair of dots means other two pairs are also dot, that is simultaneously the polarities of voltages changes. Therefore, to write it in this fashion, what should I write? First, let me write here so that the diagram is present. The MMF coming out from this cross terminal here, which are same. What will be the MMF on the secondary side? It will be IB bar into N2. IB bar into N2 will be the MMF. Then current coming in through this cross here is IB bar. So this should be equated to IB bar into how much? N1 by 2, because IB bar has its influence or flowing up to this point. So this into N1 by 2. But this fellow IC bar is flowing in the opposite direction. So this should be how much? Minus IC bar into N1 by 2. I can think that minus IC is flowing from right to left. So same thing, plus minus IC into N1 by 2. Okay. This you must understand. Then rest of the things are simple, what is called manipulation of equations, nothing else. So we have balanced this one MMF and this one. So MMF on the secondary side is IB bar into N2 coming out from this cross terminal here. Therefore, you calculate now the MMF on the left hand side, that is the primary side. So IB bar enters through the cross, it is plus IB bar into N1 by 2. And then let us assume minus IC is also flowing like this, minus IC. So minus IC into N1 by 2. These two together will balance this one. So once you get this equation, that is this second equation will be like this. That is, this is equation 1. And second equation will be IB bar into N1 by 2 minus of IC bar into N1 by 2. And this should be equal to IB bar into N2. Our objective is to calculate IA, IB, IC, of which IA I have already got. Therefore, we get one equation, IB bar minus IC bar as equal to 2N2 by N1. If I am wrong, correct me. 2N2 by N1 into IB bar. Is that correct? Okay. So this will be this one. So this is equation 2. Where is the third equation? Sum of these three currents, IA, IB, IC, must be 0. Whether balanced or not, it does not matter. Because, okay. So IA bar, the third equation is IB bar plus IC bar is equal to minus IA bar. Therefore, by adding these two, I can get IB bar. That's simple algebraic. So IB bar will be from 2 and 3. From 2 and 3. 2 IB bar is equal to minus IA bar plus of 2 N2 by N1 into IB bar. or IB bar will be equal to minus IA bar by 2 plus of N2 by N1 into IB bar. Similarly, if you do 3 minus 2, you will be getting 2 IC bar as minus IA bar minus of twice of N2 by N1 into IB bar, or IC bar then will become minus IA bar by 2, and this is minus. This will be minus 2 N2 by this 2 will not be there. Okay. So this will be this equation. So this is the IC value and this will be the IB value. And IA I have already got. Now I will place them in the phasor diagram appropriately. So what we should do? Suppose this was my primary phasor voltage diagram. This was A, B, C supply points. On the secondaries, you had got these things. This is the secondary voltage. This was your IA bar. And this was your IB bar, whose lengths are equal, theta. Now, here you can draw the currents anywhere you like by adding it. I will just draw it here at the center. So, how do I plot I capital A bar? As you know that IA capital bar is just this one. This from this one. It will be in phase with IA small bar. That is this equation. I will write here also. Ia bar we have calculated earlier is 2 by root 3 n2 by n1 into Ia bar. So what you do, you draw a line parallel to this Ia bar and get this one. The length of this one will be 2 by root 3 times n2 by n1, which is equal to 2 by root 3 n2 by n1 into Ia bar. So this I have drawn. Now I have to get IB bar. Now IB bar is the sum of two phasors, minus Ia bar by 2 plus n2 by n1 IB bar. So from this point, therefore I add first this phasor I draw. What will be this phasor? It is n2 by n1 into IB bar. So I draw a line parallel to this one. This one is n2 by n1 into IB bar. That is this one, this term I have drawn. To this I have to add minus Ia bar by 2. So you draw a line like this, half of this length, and in the opposite direction. This one is this will not come. So minus Ia bar by 2. And you will be getting your IB bar. So IB bar is n2 by n1 into IB bar, that is this phasor, parallel to IB bar I have drawn, plus minus Ia bar by 2. Ia bar is known, so minus of that. Similarly, IC bar is minus n2 by n1 into IB bar. So n2 by n1 into IB bar is there. So minus of that. So this one. And to this you have to add once again minus Ia bar by 2. So add this one. And this one will be your IC phasor. What is the angle between Ia and IB? 90 degree, because they are shifted by same. So this angle is 90 degree. So you have got, at least graphically, I know what to do in order to get Ia, IB, IC. Now I have assumed on the secondary side balanced two-phase load. What is the three-phase loads, that is Ia, IB, IC? Will they be also balanced or not? So for that, what you have to do? You have to prove that the length of this Ia, IB bar, capital IB bar and capital IC bar are equal, you have to prove. And what else you have to prove? This angle 30 degree you have to prove. 90 plus 30, 120 degree. Okay. So tell me, can you prove this one? So this triangle, this is a right angle triangle. Calculate the magnitude of this length. Okay. So you calculate the magnitude of Ia bar, IB bar and IC bar. For example, magnitude of Ia bar will be how much? It will be 2 by root 3 into n2 by n1 into magnitude of Ia bar, that is, let us say Ia, magnitude of Ia bar. This is 1 over. Now magnitude of IB bar will be square root of n2 by n1 into magnitude of IB bar whole squared plus of Ia bar by 2 whole squared, magnitude of that. So Ia bar magnitude is this one, by 2 will be how much? 1 by root 3 into n2 by n1 into Ia bar whole square. And remember, the magnitude of IB and IA are same because secondary load is balanced. So quickly tell me, after who are very good in calculations, how much it comes? 2 by root 3 n2 by n1 Ia, magnitude of Ia, which is same as magnitude of Ia bar. And obviously IC bar will be same because the component vectors are same. Magnitudes of this length is this length, this length, this length. So this IC bar will be also same. IC bar is also same. Okay. IC bar similarly will be under root of this square plus this square only. It is another right angle triangle, same sides. So IC bar can be also same as Ia bar ultimately. So lengths are equal, but balanced three-phase system demands also the angles will be 120 degree between them. So to do that, you assume this angle to be some alpha, tan alpha you calculate. So tan alpha will be how much? The magnitude of Ia bar by 2, that is 1 by root 3 n2 by n1 into magnitude of Ia bar. Ia bar by 2 divided by the magnitude of n2 by n1 into magnitude of IB bar. But Ia bar and IB bar magnitudes are same, so this is 1 by root 3. So alpha will be 30 degree. That is what I want to tell is this, that if the secondary load, so alpha is 30 degree here, this alpha. Therefore, the primary currents which will be drawn for a balanced load connected on the secondary sides, two will be balanced. They will draw same currents mutually displaced by 120 degree. That you should remember. Of course, these equations, that is knowing the value of currents on the secondary sides, that is Ia, IB are known, the load we have connected known. This Ia bar, IB bar and IC bar that we have calculated, this and this, these are most general equations and can be applied for unbalanced load also. Okay, that is in such cases it may be like this. This one graphically one can apply the above equations to obtain Ia bar, IB bar, IC bar from unbalanced Ia bar and IB bar. That is, my method will be like this. Suppose secondary side, these are the voltages, and secondary currents are unbalanced. Let this be Ia bar, and let this be IB bar of different length, different power factor, unbalanced. So how shall I calculate primary current? So Ia bar will be, of course, this equation demands this one. So Ia bar first I will draw. It will be parallel to this small Ia bar. Ia bar I will draw. Ia bar I will draw. Then your IB bar will be equal to addition of these two vectors. IB bar is addition of this and this. So then you calculate n2 by n1 into IB bar. This one, this you will calculate n2 by n1 into IB bar. And to this you have to add minus Ia bar by 2. It may look like this now, minus Ia bar by 2. And this will be your IB. Are you getting this idea? Huh? Similarly, this one will be minus this fellow and minus Ia bar by 2. Obviously, this time the current will not be balanced drawn from the three-phase side. Now, suppose you have also supply neutral available to you and you want to connect here. Where will you connect? Suppose ABC is the supply, okay, three-wire system, and supply neutral is also available, and you want to connect it because perhaps to reduce third harmonic voltages, because it is only three lines you have connected, then maybe some third harmonic fluxes induced on the secondary side also. Suppose you desire to connect the supply neutral somewhere on the primary side, where will you connect? Oh, then wrong. You have to connect here at the centroid of this triangle. Okay, so there must be additional tapping appropriately, whatever it comes out to be, you can easily calculate, and this should be connect to the neutral, not here at all. Okay, because the neutral of this three-phase system will be somewhere there. Got the point? You have to calculate this one. Similarly, you think yourself whether it is possible to transfer the voltage from the two-phase to the three-phase side. This I leave you to think over. Okay, suppose balanced two-phase supply is there. Can you get a balanced three-phase voltage? That is, this side I will energize, and can I get a three-phase balanced output? These are the things you think about. Clear? Therefore, Scott-connected transformer, the basis of the thing is the MMF balance equations writing correctly. And just to tell you, you adopt this method. It is not only true for this, what is called this Scott-connected transformer only. Whenever there will be, whether it is auto transformer, whether it is two-winding transformer, you follow this rule. The kind of problems I gave you in the exams will be, can be, or should be also done like this. Suppose you have a transformer like this. This is this secondary, and suppose this is the center tap. You have connected several loads here, or here suppose inductive load, here suppose capacitive load, like this, something like that. And these values are known, turns ratio, etc. are known. So you calculate this current, is not IR bar you calculate. This you can easily calculate from the load, IXC you calculate, and put IXC you calculate. Remember, all the voltages are co-phasal, induced voltage. Then what will be this current? This plus this I can calculate. The arrow is important. That is, in the first class I told you, the importance of phasor diagram should be understood very clearly. Once you go to phasor, you can invoke all the things that you do with DC circuit. Put also polarity markings there, then you will never make any mistake. So this is IR, IXL. So this will be this current. In this way I can calculate. Similarly, IXC, this current I can calculate. This plus this. And this is number of turns, suppose N1. This is suppose some N2 by 2. This is N2 by 2. What will be the MMF equation, balance equation? So this one current is coming out from the dot. So this will be N2 by 2, N2 by 2 into this current, that is IR bar plus IXL bar. And it produces MMF, suppose in the upward direction. Then let us calculate the MMF produced in the upward direction. This plus once again N2 by 2, and this one will be IXC bar plus IR bar, and through the dot both the currents are coming out, and let us assume this current, I assume, say I1 bar flowing into the dot. So this must be equal to I1 bar into N1. So the same technique you are applying. Don't, think in isolation that for auto transformer I have to do like this, for two-winding transformer like that, for Scott connection another technique, not like that. So that convention you must bear in mind. Now today, so this is the phase transformation thing. Now today I will tell you how to analyze three-phase circuit with the help of equivalent circuit. Equivalent circuit of a three-phase transformer. Now I will put it in this way. Suppose you are using 3 single phase transformers to make a 3-phase transformers. So for those single phase transformers, I can do open circuit, short circuit test and get the parameter values. Suppose you have got 3 transformers, identical, single phase. The parameter values of each one of them are supposed known by doing open circuit, short circuit test that I told you. Okay. Now suppose such 3 transformers whose equivalent circuits are known by doing open circuit, short circuit test are suppose connected. Let us take this connection, delta star connection. Such that I have applied V1 voltage here. Suppose rating of each transformer is V1, V2 volt. So line to line 3-phase voltage I have applied V1. How much voltage you will be getting here? Root 3 V2, root 3 V2, that you are getting. Now this transformer is now loaded, etc. like that. Now what will be the equivalent circuit? The load is balanced. Load is balanced. So what they do, or what is the common practice, is that you draw the equivalent circuit per phase basis. Equivalent circuit, per phase equivalent circuit, always you should attempt per phase equivalent circuit. So what I know for this transformer, I know RE, R1, this series part, leakage reactance X1, this secondary side R2, JX2, whatever it is there. Now suppose I want to draw per phase equivalent circuit, refer to side 1. How will you do? I will draw like this. Per phase voltage is V1. I will solve a problem next time, but you just try to get the idea so that you can follow next time. So per phase voltage is V1. I will draw. Now what is the per phase impedance? Here it will be RE1 plus JXE1 I will put. And per phase parallel branch I will put like this. This will be my per phase equivalent circuit referred to side 1 or delta side. And when you draw the per phase equivalent circuit referred to the star side, in this case, how it will look like? Are you getting the problem? Suppose these 3 single phase transformers whose open circuit, short circuit have been performed, and I can calculate for this transformer the equivalent circuit parameters refer to any side I like. So that I am doing. So per phase you do like this. Similarly on the LV side, if you want to draw, what voltage you should show here? Per phase voltage will be V2. And these values should be this winding parameters referred to that side, JXC2. And here it will be this parallel branch. And this transformed values on this side, only thing to remember, don't multiply or divide by the line to line voltage ratio. The actual winding turns ratio, that is phase voltage ratio, you should take into account. Okay, tomorrow I will take that problem, a numerical problem. But today I will just give you a small problem. You just suppose how you have understood the rating of a 3-phase transformer. Suppose you write down this problem. A transformer is rated as 100 kVA, say 5000 volt. 400 volt, 50 hertz, 3 phase, and the connection is given to be star delta, okay, star delta. Assume the transformer to be ideal, assume the transformer to be ideal, okay. A three-phase load of say 70 kilowatt, 0.8 power factor lagging is supplied at 400 volt. Calculate currents, in all parts of the circuit. In all parts means all the windings, all parts of the circuit. So what is the situation? You should draw a circuit diagram. Star, and this side is delta, and here is a three-phase load. Unless otherwise specified, tell me this voltage, line to line voltage, that you must remember. So this applied voltage is 5000 volt. This voltage 400 volt, line to line. So what will be your first step? Calculate this current, this line current, and this is the total power at line to line voltage. How will you calculate current? Root 3 VL IL cosine theta, that you must remember. Root 3 line to line voltage, line current into power factor. From that you equate it to 70 kilowatt. You will calculate this current. So first calculate this current. After calculating this current, what you will calculate? The winding current you will calculate. Don't make any mistake. This current, then this divided by root 3 straight. Then what you will calculate? This winding current I know. So what will be this winding current? This turns ratio you have to take, what I am trying to tell. And then you will get the magnitude of the current of this phase. So today I stop here. Next class I will see.